Okay, so we're already at our final slammer. The final slammer we've got is Emily Sonnex. Emily's a final PhD student in the Department of Chemistry. This last slam was probably the messiest as well, so it might take a little time to clear it up. Emily's research looks at applications of infrared spectroscopy in forensics. In her spare time, Emily is a brownie leader and an amateur dressmaker. Emily's slam is entitled Chemistry in the Fight Against Crime, and the introduction is thus. Good quality forged banknotes can baffle forensic experts and pass by the eyes of shopkeepers. However, if we look closely at the chemical composition of forgeries, we can find vast differences which are invisible to the eye. Chemists have a wide range of techniques that can be used quickly and easily to spot these forgeries. Emily's slam will show you exactly how. So if we're ready to go, I can invite Emily up. Please join us. Big round of applause. Slam will start on Hillary's bell.
How do we know that this £20 note is real? Well, this tells us. But what on earth is this? Well, this is an infrared spectrum, and it's produced by an instrument called an infrared spectrometer. But what is that? Well, it's a fancy bit of equipment. It's a bit too expensive, so I couldn't bring it along here today. But how is it produced? Well, let me start from the beginning. So we all know that atoms can vibrate. Remember solids, liquids and gases? The more you heat up some atoms, the more they start to move around as they gain more energy. But as well as this, the bonds between the atoms can vibrate as well, but they do this in a more uniform way. I think to demonstrate this, I'm going to need 3 volunteers from the audience. Anyone? Yeah. 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 Oh, okay, so I think we've got 3 people here.
No, you go.
Did you come up on stage? Okay, if you just come along the front here to the steps. Okay, so what are your names?
I'm Jack.
Jack?
Oliver.
Oliver?
Adam.
Okay, Adam. So if you move on stage a bit. Okay, Adam, I don't need you just for a second, so if you just step to one side. Okay, so do you 2 know each other at all? Okay, well I need you to hold hands for me, so you're going to get to know each other. Okay, so you're my atoms. So you're going to be a molecule of carbon monoxide. So we're going to have a carbon atom and an oxygen atom. And where you're holding hands, that represents your chemical bond between the 2. So these atoms can only vibrate in one way, and that's by moving apart from each other and then towards each other. So can you demonstrate that for me? So if you move apart and then back and then keep going. Perfect. Okay, but what if you had 3 atoms? So that's where you come in. So do you want to hold hands as well? Perfect. Okay, so now you're going to be a water molecule for me. So water is made up of 1 oxygen atom in the middle with 2 hydrogen atoms on either side. Got that? But a water molecule doesn't stand in a straight line. It's slightly bent like a V shape. So if my 2 hydrogens on the end can move forward slightly, so you make a V shape, perfect. Okay, now this molecule can vibrate in 3 ways. The first is a symmetrical stretch. So that's where the 2 hydrogen atoms move forward and then back. So if you step forward to the front of the stage and then back again, perfect, you keep going. Okay, then we've got an asymmetrical stretch. So that's where 1 hydrogen moves forward first and the other one moves back, and then you swap over. So Jack, if you move forward first, and if you move back, and then you swap over. Perfect, so that's asymmetrical. And then finally, we've got a bending stretch. So that's where the 2 arms of the water molecule, so the 2 hydrogens, move inwards towards each other like that. Yep. Perfect, so you keep going. Okay, can we give a round of applause? But what if we had more than 3 atoms? Well, it would get far too complicated and there'd be so many more vibrations, it'd be impossible to show on stage here. So the vibrations that we just saw vibrate at a certain frequency, and that's how fast they vibrate. So we had a water molecule there. If we had carbon dioxide instead, So there would be one carbon atom in the middle, 2 oxygen atoms on either side. It would vibrate at a different frequency, even though it's still got 3 atoms. So what happens when we get our sample and put it into an infrared spectrometer? We pass a beam of infrared radiation through it, and if the frequency of the radiation exactly matches the frequency of the vibrations in the molecule, it will get absorbed. So then what passes out the other side will be slightly different. And that's when we get peaks on our spectrum, like these ones here. So I can demonstrate with this torch. Okay, so the light from this torch looks white. It's actually in fact red, green and blue light. We just see it as white. But if I pass this green film over the top of it, it looks green. And that's because the red and the blue parts of the light have been absorbed by the film. And that's just like what's happening inside our infrared spectrometer. So if we had a simple molecule, we'd only get 1 or 2 peaks in our spectrum. But when we get a complex molecule, we get lots of peaks. And I should probably point out at this stage that the peaks actually point downwards rather than upwards, just to confuse you. And where those peaks come on the spectrum depends on the type of atoms that we've got or the type of vibrations that we're looking at. And those peaks are unique to that molecule, just like its signature, and that means that we can use it to compare things. Now this makes it really useful in forensics, because we can compare something that might be forged to something we know to be real, like our banknote. So the spectrum here is from a forged banknote. I'm going to draw for you now what a real banknote would look like. Okay, so you can see that the two look slightly different just here. So if we know what the real banknote should look like, we know when we've got a forged banknote. But it's not just limited to banknotes. We can look at works of art, archaeological finds, fibres from crime scenes, absolutely anything. And that is how chemistry is winning the fight against crime.